In the last class, we had discussed the buses which we expect to find or we expect to implement in an SOC. We have also looked at serial buses, and we had started discussions on one of these buses, that is I2C. Today, we shall continue the discussions on I2C and look at other serial buses as well. First, let's recapitulate the I2C basics that I had done in the last class. I2C is basically a two-word bus. It has got two lines, serial data line and the serial clock line. The voltage levels are logically high and 0, that is low. The bit transfer takes place when your SCL is 1. So, SCL 1 implies that SDA line now has a valid data. So, you got to have valid data when the clock is high, and data change can take place, the transitions on the data line can take place when your clock is low. So, basically it is a two-line bus, and using two lines there can be number of devices hanging one after another, and they can communicate data with each other using just two lines. So, here the data transfer is in a bit serial fashion, and that is a basic difference with any of the parallel buses that we have seen so far. So, I2C lines can have two possible states, okay? What we say a float high and drive low, and pull up resistor on the line are connected and only devices pull the line low. So, if no device is pulling on the line, it will float high. That means by default the I2C signals will be always high. So, what is really this interfacing circuitry? Here you will find that I have shown two such blocks. If you look at it, that these are the two lines, this is corresponding to the SCL and this corresponds to SDA, the serial data line, and there are two devices hanging from these two lines. So, here the serial clock is connected, okay, and this will be the internal input to the device, and this is the out and this is basically in. So, what does that mean? That means that when it is driving, when this device is intending to drive the bus, the clock should be generated by this device, else it will get the clock in, that is a clock which is currently on this line being generated by some other device. Similar thing is true for the data line, that is SDA line as well. So, these are all open collector interfaces or open drain interfaces. So, you have got the resistors connecting these lines to the VDD, that is drain voltage, so that the normal condition for all of them is high, and effectively this connection is nothing but wired ending. So, a device can pull the line low. This is the basic structure and interface of the devices for connecting onto the I2C bus. Now, when the transmission is to take place, there has to be start condition and stop condition. Start condition is when the SDA line makes a transition from high to low when SCL is high. Okay. So, when the clock is high and SDA is making a transition, it means there is a start of a frame, that is a frame of data that is being transferred. The stop condition occurs when there is a transition from 0 to 1 and when SCL is high. So, these two states, this is S and this is P, the stop condition. There can be also another state, what is called a repeated start. So, start is generated instead of a stop after a frame. So, bus is normally busy after S and before next P, and free after P and before next S. So, this actually indicates beginning of a data frame which is to be transferred. So, what happens in data transfer? Data bits are therefore transferred after start condition, and whole transmission is byte oriented. So, one unit that you transfer is 8 bits, but that is considered as 8 bits data plus 1 acknowledge bit. This acknowledge bit is to be transmitted by the recipient of the data, and the order in which data is sent is that the most significant bit is sent first. In fact, since there are multiple slaves which can be connected onto the bus, we need a mechanism to identify the recipient of the data. So, address of the slave is also data. In fact, the first byte after this transition, when you start transmission, is actually an address. During the first byte, the master is a transmitter and addressed slave is a receiver. And next bytes depend on last bit in the address byte. So, depending on whether it is a read operation or write operation, either it will be master transmitting the data or it will be the slave transmitting the data. The recipient will always generate the acknowledge bit after transmission of 8 bits. So, this is the basic addressing scheme. There are 7 bits which is used for addressing the slave devices. So, each slave device can have a 7-bit address. The 8th bit is basically the direction which tells you whether it is a write or read. Master may generate repeated start, okay, and address another device. That means the bus still continues to remain busy. Each device listens to address. If the address matches that of the device switches state according to its read or write bit. Read or write bit as part of the data which is getting transmitted from the master. So, what is exactly the synchronization takes place? The master sets SCL 0 and generates pulse for each data bit, okay, and 8 pulses for data is to be followed by 1 for acknowledge. So, here master's responsibility is to generate the clock, although the acknowledged data will come from the slave, but master will be generating the clock because it is driving the bus. After acknowledge, the master tries to generate next byte's first pulse. The slave can hold SCL low, okay. So, if the slave holds SCL low, then the master will switch to wait state because it cannot send the next data because device is not yet ready to receive the data. So, that ready condition is now being provided by pulling the clock low. So, pictorially if you look into it, so this is basically the transition which is taking place from 1 to 0 when my SCL is high, which is indicating that a data frame is starting, okay. Followed by this, there are these clock pulses which are being generated by the master, and this data is being sent with the most significant bit first. Now, at this point corresponding to this clock, the master does not send any data, okay, and here actually the whole reason is why master is not slaving, because it is really waiting for the acknowledge to come from the slave. after this, what happens? The slave will pull down the clock, because slave would like to now have a wait state, because it may be using an interrupt, slave may be using an interrupt call to transfer the data or do anything, any other housekeeping task. So, it introduces a wait state here. So, when there is a wait state, effectively no data is sent. Again, the clock starts pulsing at this point, and from this point onwards the data transmission can start. Okay. And here what is being shown is that after that there can be a restart or a stop condition. That is depending on how your SDA line is going through a transition when your SCL is high. So, this is exactly how the data transfer is coordinated by the clock, the master clock. Now, the data bits which flows along your SDL, okay, serial data line, is generated by the transmitter. Now, transmitter can be master or maybe the slave, depending on whether it is a read or write operation. In the 9th pulse, okay, the transmitter releases SDA. The receiver must hold SDA low in order to acknowledge the received data, okay, and slave must release SDA after the acknowledge bit, okay, so that now the master can again start transmitting, provided clock is not pulled low by the slave. So, now if we see the waveform, if it is the same thing, so what you are finding here, this is acknowledgement which is coming. So, this acknowledgement here, the SDA line is now pulled low by the slave, and this is corresponds to this clock pulse which is generated by the master. So, the frame format is, you have got the complete frame format is, you have got the start transition, you have got the slave address, then you have got the read write bit, okay. Then actually you start the address. Now, here A is the acknowledgement which comes from the slave. So, after your first byte which indicates address, you got to have an acknowledgement from the selected slave. If no such slaves exist or currently connected to the bus, then obviously the acknowledgement will not come and the frame has to be aborted. So, this is exactly how the whole frame format looks like, and the master receiver is since the second byte onwards, this effectively similar. So, you have got the data which is getting transferred and with the corresponding acknowledge. Now, I2C is basically a multi-master bus. Okay, so, in that I2C bus, there are multiple devices which are hanging from, and they can take up the role of master or slave in an interchangeable fashion. Okay. So, there could be multiple master which can be there on the bus. So, you need a mechanism for bus arbitration. Now, any one of several different devices which are there on the bus may act at the master as a master at various times. And what you have observed, I think by now, that there is no global master to generate a clock. In fact, the device which is currently driving the bus becomes the bus master, and the master drives both SCL and SDL as the case may be. Okay. Now, when two devices try to drive SDL to different values, there would be actually a conflict. Okay. So, what it is done is, the device can listen to the bus to be sure that it is not interfering with another message. Okay. That means if a device is trying to send a logic 1, but hears logic 0, it will immediately stop transmission and gives the other sender priority. So, the moment it detects a conflict, okay, it would withdraw. Okay. The whole logic, the hardware should be built in such a way that when the device is withdrawing, it is not really disturbing the data which is passing on the bus. And after some time, again it should be tried out. This is the basic scheme of the bus arbitration. So, if you look into it, that this whole arbitration implies that there is a synchronization with respect to SCL, okay, because all these decisions are being made with regard to your SCL and SDA lines. So, what is being shown here is the SCL and SDA line of the bus, and these are the data may be coming from two distinct devices. This is your data 1, okay, and this is from data 2. Now, what you are finding here is that the data, when it is going through at this point, both the devices are generating identical data, okay, corresponding to this clock. So, now since the data is identical, there is no way to detect a conflict. There is no way to detect a conflict. So, the other device which is sending it, it will not detect a conflict, and it may assume that the bus is with it only. Now, what happens is that when it comes to the next one, there also you will find no conflict. The conflict comes in at this point only with respect to this clock. Okay. So, here there is a mismatch between the data 2, which is currently driving the SDA line, and it is finding that this is the data is high. So, it cannot drive the line, and hence it would realize that there is a conflict and it should relinquish the bus. Now, obviously, this whole logic works out with respect to a synchronized clock, because all these transitions, I told you that data valid condition is when your clock is high. If the SCL is not synchronized for these two, okay, and if two devices start issuing non-synchronized SCL, then there would be a problem. So, obviously, bus arbitration requires a step for synchronization on SCL and then the arbitration on the serial data line. Now, I2C is available, the hardware for I2C is available in a variety of PIC microcontrollers, okay, in variety of microcontrollers and in PIC family as well. Typically, this MSSP module, which is there in PIC, provides the support for I2C. Now, the basic structure is that in the I2 MSSP module, you have got this I2C engine, okay. You have got these two registers, SSP buff, this is a register. So, this is the master and this would be the corresponding peripheral. Peripheral should also have the I2C engine, otherwise it cannot communicate following I2C protocol. So, it has got the control and the control logic as well as the action part. So, effectively this I2C engine implements I2C protocol in hardware. This SSP buff is a register that stores data sent or received on I2C bus, because there will be serial data. So, it has to be stored and buffered, and this control controls action of the device based on I2C instructions. Now, try to understand the difference between the functional role of I2C engine and that of this control. okay. Because if you remember, I said that if I have let's say a data frame I have started, okay, and I want to read data, the master wants to read data. So I2C engine will detect that this is a read operation, and depending on that read operation, the control logic has to be activated to provide data on the serial data line. So this is this control logic, okay. So control actions of the device based on I2C instructions. In fact, in a more general case, if you remember, I said that I2C bus has been used as a control bus for connecting onto various peripheral devices. So if the peripheral devices has got a set of commands, okay, then those commands will be transmitted via the I2C bus. They will be detected by the I2C engine and passed on to control logic so that there can be device specific action, okay. Now the most interesting thing that we have seen therefore with respect to the I2C is that it almost provides all the capabilities that you typically find in a parallel bus, although the bus is essentially serial and based on just 2 lines. The basic point I was making is in terms of the footprint that is being satisfied in this case. So on a board, if I want to connect my PIC microcontroller with say another device and use a small footprint PCB, a desirable feature would be to use I2C bus, because I have to just put in 2 wires to connect a variety of devices, a variety of peripherals to my PIC microcontroller, okay. And it has got the complete logic for bus arbitration, which you typically find in a parallel bus as well. So what are the advantages? Advantages is good communication with onboard devices that are maybe accessed occasionally, because if it is being regularly accessed, okay, say a cache memory, obviously I won't like to use a serial bus because that would be delayed. But if you remember, I said that in PIC, E2PROM has got an I2C interface, okay. Why? Because E2PROM will be typically a program which is stored, which may be downloaded onto a RAM for execution, or some bookkeeping data would be stored on the E2PROM. So these are occasional reads and writes, okay. It is not on a regular basis. Now this bus is easy to link multiple devices because of its addressing scheme, and cost and complexity do not scale up with the number of devices, because you still continue to use simple 2 lines and you connect an additional device onto the bus.